Okay, this is seriously my favorite part about Chemistry 11. Different types of equations. So awesome. You get to look at it like a puzzle. You're looking at the equation on the page and you're going, oh, I gotta find the pattern. I gotta figure out what's going on here. And so you have to understand what patterns we need to look for when we're identifying what type of reaction that you're dealing with. So we're going to establish kind of a key with basic symbols, and then we'll go into actually using particular elements and compounds later on. Now the first equation is synthesis. And synthesis, by definition, means you're making something, creating it. So what we're going to have is a couple of building blocks that we put together and create something new. Now, it's easy to identify a synthesis equation because you're going to have more than one reactant, but only one product. A decomposition reaction, it's decomposing, it's falling apart. It's the exact opposite of a synthetic or synthesis reaction. So you'll start with a compound, and that compound will come apart into smaller pieces. So that one should be pretty easy to identify as well, because it's the opposite of a synthesis. You have one reactant, more than one product. Now a single replacement reaction is a little bit more complicated. You're going to have a compound, so I could have a compound like AB, and generally speaking, we've got a metal and a non-metal, and they're going to combine with another metal. That's typically how this goes. What you're looking for is one compound and one single element. And what happens is, because these would be both metals, they would switch places. Now I'm not going to have two metals come together, because metals don't bond with each other. They're both positively charged. And also, if this is in this position, it's going to be a negatively charged, so the negatively charged ones aren't likely to do that at this level of chemistry anyway. So we'll end up with, if it's at the first part of the equation, it's going to stay in the first part of the equation, and that's where the metal goes, the positive ion. So if this is a metal, then it's going to switch out with this metal, going to knock it out of the compound so that this guy's all by himself. So I'm pretty sure that in Science 10 we talked about, there's a cartoon in your book as well where Buddy gets ousted by a better looking guy and his girlfriend leaves him for somebody else. That's what a single replacement is. You're single now, you've been replaced. All right, double replacement is a little bit more complicated. You've got a compound and another compound. And what happens here is it's like a little dance move where you switch partners. So A and C are the metals, B and D are the non-metals. A and C will switch places, and you'll end up with two new compounds. But the important thing to remember here is that metals switch with metals. They don't bond with metals. And nonmetals are the same. They switch with nonmetals. So if it's in the beginning of the compound, it's going to remain in the beginning of the compound. If it's at the end of the compound, it's going to be at the end of the compound. So keep the places when you switch them. Never put, for example, never put B and D together in a new compound. Never put A and C together in a new compound. It doesn't work that way. Remember, positive charges, negative charges. Positive and negative have to combine, not positive and positive or negative and negative. So this is how she goes. All right, now in acid-base neutralization, we're getting specific now. It's a specific type of double replacement. And what we have is an acid. So you know that hydrogen is not a metal per se, but it's a positive. So hydrogen will be in the beginning of any formula, and it will have a negative ion attached to it. Now we'll have another positive ion that's attached to a hydroxide ion, which is a negatively charged ion, OH negative, and we end up, uh-oh, that's no good. Better. We end up with the same idea. We have a double replacement, so this guy's going to knock this guy out and make HOH, which I'm just going to write up here because usually we don't write it like that, we write it like this. Oh, hey, look, it's water. So water is going to be a product of every acid-base neutralization. So that's a really easy way to identify that it's an acid-base neutralization. Water's a product. And we'll also have, seriously? Just up with my markers. Anyway. We're also going to have this combination where C is in the front, so it stays in the front, and B is in the back, so it stays in the back. We've got a positive and a negative ion coming together. They are not an acid or a base because they don't have H or OH. They just have the metal and the nonmetal. So that's what's called a salt. If it's an ionic compound and it's not an acid or a base, it's a salt. It will have a metal and a nonmetal, and there it is. So, very specific. We have an acid, which we can tell it's an acid because it has an H in the beginning. We have a base, and we can tell it's a base because it has an OH at the end. We have water, and we have a salt. You can't really get too much more complicated or specific than that. Oh, wait! There's one that's more specific. Combustion. Combustion is our last one, and it's quite specific. So a combustion reaction will have, I'm just going to write X and Y here because it doesn't really matter what the numbers are. What matters is that it's a carbon and a hydrogen. And once in a while there might be an O or an S attached to it as well, but it was always have carbon and hydrogen, and it's called a hydrocarbon. Makes sense? Hydrogen, carbon, hydrocarbon. Now, that includes any of the fuels you can possibly think of. Wood is basically cellulose, which has C's, H's, and O's in it. Butane, methane, propane, those are all hydrocarbons. They all have a different number of carbons and a different number of hydrogens, but that's pretty much all they are. And so those are the fuels. Hydrocarbons are our fuels. They burn in the place of, or in the presence of, oxygen. So oxygen is the next thing that we always have present in a combustion reaction. We have to have oxygen in order for it to burn. Now the other thing that's really specific is what happens as a product of this. We're going to get energy, yeah, but for the most part what we've got is water. So there's our C's and O's. And carbon dioxide. Sorry, those are H's and O's. Those are C's and O's. C's and H's and O's. That's what combustion is about. I have my hydrocarbon combining with oxygen. We need to have the fuel and the oxygen to burn. It creates water, which you may not regularly think of something burning, creating water, but think about if you're into being around vehicles and stuff, sometimes you'll see water dripping out of a tailpipe. That's because it's a combustion reaction that's happening. It creates water. Actually, when you burn wood, it also creates a certain amount of water that goes up as steam as you're burning it. So we've got water and carbon dioxide. We all know that another kind of combustion is inside of you. You are you're freeing up energy when you're digesting sugars, and you have to have oxygen to do that, and you're creating carbon dioxide, which you have to breathe out. So there's lots of examples of combustion in everyday life, and they all follow the same pattern. Hydrocarbon, oxygen as reactants, water, carbon dioxide as products. Once in a while, you're going to get something a little more complicated. Might be an O or an S or both attached to here. There might be a sulfate or a sulfide as a product. But this is the basis. You see this? Combustion every time. So those are your 6 types of chemical reactions. These are the patterns that we need to remember in order to identify them. And now we're going to get to actually using real elements and compounds.